Thanks for the introduction. So this is a joint work with Maxime and Jean-Pierre about trying to find trade-offs on algorithms to solve the Dihedral Coset problem, which is also, well, basically we're solving the abelian hidden shift, and it's also sometimes also the Dihedral hidden subgroup, but basically it's the same thing. Okay. So basically the algorithm we want to solve is when we have an abelian group and two functions defined on this group with values into a set, and there is a shift between them, S. So f of x is equal to g of x plus s. I want to find this shift. Now, this problem, interestingly, underlies the security of crypto based on group actions, which is proposed for post-quantum crypto systems like CSIDH, or the proposal we had presented this morning. So in this talk, I will simplify things and consider G, the group, to be Zn for some big N. Okay, what does it have to do with what we call the Dihedral Coset problem? We're going to go there, and for this we have to do some quantum stuff. So quantum 101 in a single little block here is basically that we operate on states which are superpositions. In these superpositions, you have complex amplitudes. We can't do anything with the amplitudes. They are not observable. We know that when measuring this, we can observe an x with some probability, which depends on the amplitude. But otherwise, we have to do operations which modify the amplitudes in order to find a good x when we observe. So going there, we start from a superposition that we create, and we put a superposition of all elements of Zn in this. And then we apply the function, which is either f or j, the shifted one, depending on a bit that we put also in superposition. And at this point, we obtain a state in which you have x and images of f and images of g, and we measure the output register so that we will obtain something in which you have everything that has this image, which means, assuming some injectivity, an element x, and then the shifted one, x plus s. Well, we also don't know x, but we have a state of this form, and it contains some information about the shift s. And basically, what we call Dihedral Coset problem is finding s when we have such states which are given with random elements x, which is why we arrive here when we try to solve the abelian hidden shift. Now, actually, the algorithms that solve DCP, they don't, well, they have to do something else first. They have to convert these vectors into what we call phase vectors. So phase vectors are going to encode some information about the shift S into a phase, which means an amplitude which is of modulus 1. And the operation to get there is to apply a quantum Fourier transform, which is an efficient operation, and basically just maps x to a sum of all omega n power kx k. So superposition of that, and omega is just the standard value here. So when we have done that, we measure the register, and we're going to obtain this. We're going to obtain a superposition of 0 and 1, and the 1 is slightly dephased with a phase that depends on x. There is information there. It's not immediately observable, of course, because, well, if we observe that, we obtain either 0 or 1, right? And we also obtain the value k. So now we have these phase vectors. We know the k. We are looking for the s, and the s is hidden in there. And all the algorithms we know for DCP and for abelian hidden shift, and basically for breaking C-side or so, they combine random phase vectors into useful phase vectors. And useful means we can put some constraint on the value k. And with this constraint, we can observe information on S. For example, let's say n is even, and let's say you obtain the label k equal n over 2. Then the phase vector is simply 0 plus 1 or 0 minus 1. And you can distinguish that. So you can obtain 1 bit of S. There are many algorithms out there to solve the problem, and they're all doing trade-offs. They have many possible trade-offs, actually. So one of them is the Ettinger-Hoyer algorithm, and it has n queries, and due to the n time complexity, a bit large. Cooper-Beck's algorithm in 2003 reduces this to sub-exponential query and time complexity. Regeff's is also a sub-exponential algorithm, but it has a smaller memory complexity. And Cooper-Beck 2011 is the best in time, and it also has like 2n queries and time. But there are many, many trade-offs with these algorithms to attack, for example, to attack C-side instances, especially trade-offs where you can reduce the memory complexity, which is what we're interested in. So in this paper, we presented an algorithm with linear query complexity, which is improved in time with respect to the Ettinger-Hoyer. And we showed that you can interpolate between this algorithm and Cooper-Beck's algorithm from 2011 in a natural way that I will just quickly present. This has still limited impact on C-side for the following reason. Quantum subsetting algorithms are not as good as we like. Basically, we managed to reduce the amount of queries, but there is a term that increases, and we would like to keep the whole time complexity small. And if you manage to find better quantum algorithms for subset sum, you would improve the attack on C-side. OK, so how does this algorithm work? And for this, I need to speak about the combination routine that is used in Regeff's algorithm. So recall that all this is about combining the phase vectors in order to obtain useful values of k. And Regeff does this as follows. Imagine that you have many values of k, many phase vectors for values of k. And you want to create a new one with some condition, and this condition is basically going to be k is divisible by some great integer. So you write all of them together, all these phase vectors. There are single qubits. So if you write all of them together, you obtain a quantum state with this superposition. And this superposition, you have all the B, which are saying choices 0 or 1 if you have the label ki or not, and a corresponding phase, which is basically depends on b dot k, the vector of all the labels. So we haven't done any operation at this point, but it's still the starting state. And now we're going to do something. We're going to compute this key.b modulus b, and we measure the value that this takes. When we measure the value, we force the quantum state to collapse on everything that agrees with this value, which means we get the superposition where all the b agree with the observed value. Imagine that you did everything right, and you did it so there are two vectors b, b1 and b2. So you have the states, and there are only b1 and b2 that remain, and they have the phase, the corresponding phase sb1.k or sb2.k. And this corresponds to a new phase vector. It's up to a global phase, but global phases don't matter. So you have your new phase vector, and actually the new label here is divisible by b, because that's what we force it to do. So this is how it works for Regeff's algorithm. The idea is, in general, you can use this in multiple levels. You take a bunch of labels, you create a new good label, for example, a label that will cancel square root of n bits, and then you repeat that on multiple levels. Of course, there is something that is difficult here. It's computing the labels b1 and b2. At this point here, you have to compute the two vectors that have the corresponding b.k, and this is a subset sum instance. Given the vector of labels, find b that agrees with the value z. So, well, it doesn't really matter in Regeff's algorithm. You can do it with any algorithm you want, even like exhaustive search, because in the end, you do it in square root of n steps, basically, and you obtain a complexity which is square root of n to the square root of n. You would have a sub-exponential thing. But you can also be very aggressive on the query complexity, and you say, well, I will just combine n phase vectors, and I want to collapse immediately, I want to obtain immediately a single, like a fixed value of the label. And with this, I will recover 1 bit of S and repeat afterwards for the other bits. And you obtain basically an algorithm with n squared queries, but a larger time, of course, because you need to solve a large subset sum instance. But that's a very good trade-off when you attack C-side 512, because C-side 512 has a very large cost for the oracle for computing this query. So you want to do as little queries as possible. So how to be even more aggressive than that? This is the idea of the new algorithm that we have. And it's actually very close to what we do in Regef's algorithm, but well, a bit more aggressive. So the goal is to reduce the number of queries to linear, big O of n. But we want still to keep the time very, very like, small as possible. So here is the idea. As before, we can start by having all our phase vectors and then computing the k.b modulo something, modulo n in that case. And then the problem is, well, before we were measuring this value and then working from here. And here, we're not going to measure it. We are going to directly erase it. Well, exactly, we actually erase b, not k.b. We're going to keep k.b, but we erase b here. And how to erase b? Well, basically, we have to solve the subset sum problem again. This allows you to erase b. So you obtain just a superposition where you have k.b in the elements. And this is more or less equivalent to having a superposition, as I wrote here, over x, with the omega n to the sx here. And if you apply a quantum Fourier transform on that, you obtain exactly s. So you measure it and you get s with a single, step here, with a single pass and only n queries. Of course, there are some technicalities. The first, several technicalities. There are some errors that you have to handle, but also the fact that here we need a quantum subset sum solver, so an algorithm that solves subset sum in quantum superposition. It exists. We just need something that will solve our instance. There are also some cases where this is going to fail, and we have to handle that. But otherwise, this is the main computational cost in this algorithm. Fortunately, you can reuse some work that already exists on the subset sum problem. You could use Grover search here, but that's very easy. But you can actually reuse some quantum algorithms for subset sum, except that the previous quantum algorithms were mostly concerned in solving an instance that is given to you classically with quantum algorithms, and not an instance that is partially quantum, because target here of the subset sum is quantum, and solve it with a quantum algorithm. Unfortunately, the standard algorithms for this problem can be adapted. So we can reuse a procedure that uses quantum accessible memory if you like quantum accessible memory. If you don't like it and you want to use only purely classical memory, you can reuse the algorithm that Hellman May presented at PQCrypto a few years ago. And actually, we improved a bit this algorithm to obtain like a slightly better time and space. Okay, so now in the time that I have left, I will present a bit the idea of the trade-off that comes with this algorithm. So here it is. Imagine that instead of having any labels at the beginning and then a very hard subset sum instance, you could somehow shape the labels. This is the labels, this is a bit writing of the different labels. You could somehow shape them, so force some bits to be 0 here, like this. This would make the subset sum problem a bit easier. And depending on how many constraints you can put on these labels, so how many bits you can put to 0 here, the subset sum problem is going to be, well, easier or harder. The instance that I just presented, the linear queries algorithm, is a case where you don't preprocess anything. You have random labels, and you have to work with that. So you solve a very hard subset sum instance, and it gives you the complexity of solving the subset sum that I just gave. The easy way, the easiest setting is when you have this kind of diagonal matrix with all the bits of the labels. So the first one can be unconstrained, but then the second one has 1, 0 bits, and then up to the final one is just 1. This makes the subset sum instance trivial. So you apply this algorithm, the linear queries algorithm, but with these preprocessed labels. And of course, to obtain these labels, well, you have to use combination routines. And basically, you have to use your favorite algorithm that does that. You could use, for example, Cooper-Beck 2011 algorithm. And basically, this case is when you try to optimize using Cooper-Beck's 2011 procedure to recover the entire secret. This is what you obtain, square root of n times to the square root 2n. But in general, you can end up in the middle, and you will combine a quantum subset sum instance and then some preprocessing of the levels. Okay, so now I get to a conclusion of this talk. So, so presented in this work a new way to solve the DCP, but DCP here means also abelian hidden shift and dihedral unit subgroup with a linear number of queries, which is interesting if you want to optimize aggressively the number of queries you make. This gives also a new natural trade-off for sieving algorithms for DCP, which goes from this linear query case to, well, up to the sub-exponential query case. And in the meantime, we also worked a bit on how to solve this subset sum black box and improve the Helm-May algorithm that does that in superposition. Fortunately, unfortunately, quantum subset sum algorithms are still not that fast. If they had like a square root speedup like Grover search, it would be great. We could directly apply this to C-side. Here, we have to wait a bit until they get a little better to use the linear queries algorithm for small C-side instances. Thank you for your attention.
Comments, questions? I see here one on the left.
Yes. So if you take a classical heuristic for a subset sum that takes a random seed as input and tries, you can speed that up as a black box using Grover, right? So did you try to compare that to the other approaches?
I'm not sure which case are you talking about.
So
the classical.
So let's say you have a classical function that takes a random seed and then produces a guess for the best. Tries to find an outcome using a random seed, a probabilistic classical algorithm.
Yes.
And so then you can use Grover to look for that seed that will find a solution. So
Yes.
then you can, if your classical algorithm has success probability P, then your complexity kind of quantumly becomes square root of 1 over P.
Yes.
So did you look into that to compare to the other quantum approaches?
So this would be this would be like a trade-off that you could try to put into place when solving subset sum in general with quantum algorithms. But I don't think it would be competitive with the current optimizations we have of the, because basically classically we have this family of representation-based algorithms starting from Hofgrad, Graham, and Drew that solve subset sum, and And yeah, no, I don't think it's competitive. Like you could try to do that. I'm not sure entirely what it would do, but I don't think it's currently competitive with the approaches with the optimized algorithms we have.
All right, thanks.
But it's possible.
And we have a second question on the right.
I'm going to ask the completely opposite question to what the previous person asked. Grover's algorithm has the property that it is actually inherently sequential. That is, say, if it finds an answer in order complexity to the square root of n, or square root of n, then it takes square root of n sequential steps. And if that n is significantly large, that may be impractically long for the attacker. Have you taken that into account?
No. As a short answer. You can take that into account if you can try to re-optimize the quantum subsystem algorithms. Everything in this talk is very malleable. So you can work a bit on the DCP part, on these combinations subroutines. But in the linear case, you don't do anything anymore, you just have linear queries. But then you can also try to work a bit on the subsystem part. I confess, I don't think there is much work on what happens if you want to distribute the algorithm and use less sequential time. In our case, for small seaside instances, already the part with the linear queries uses also long sequential computation, which is making the query. So we would already have to work on that as well.
Okay, thank you.
Any further thoughts? I think we have time for one more question.
Yeah, so if I recall correctly, the regev thing was originally for lattice problems, right? And but not applicable with the Kuiperberger sieve due to some failure parameter thing. Does this trade-off have an impact on this failure parameter, or you know what I'm talking about?
Yeah, I'm not sure which regef paper was
for
about,
the Dihedral Coset problem.
Yes.
I think the first with the quantum algorithm for lattice problems to solving the subset sum.
Yeah, so that might be the regef's reduction from lattice problems to
the Dihedral Coset problem.
yes, yeah.
And but that does not lead to a sub-exponential time algorithm with the Kuiperberger sieve due to some failure parameter stuff,
Yes,
right?
indeed.
And does this linear query stuff mean that you can do stuff with some failure parameter as well?
Yes.
So.
I absolutely don't know.
Okay.
Yeah, maybe we can take that offline.
All right, let's thank André again.